Hello students, video 9, part G. Let's practice everything we learned. Another example. Summary statistics for data relating latitude versus January temperature, 50 large cities in the United States. So the X variable is latitude. Latitude is the north-south measurements. How far are you north of the equator? So the further you move north in January, typically it does get colder. We're trying to predict January temperature. That would be our Y variable. We had 50 large US cities. Two variables look to be linearly associated. Now in this problem we're just given summary statistics. We don't get to have our hands on the data or to see a graph. But at least we're told it looks linear. Based on the scatter plot, the correlation is pretty darn strong. We've got an R equals negative 0.894. The negative makes sense. The further you move north, temperature tends to decrease. There's a negative relationship between X and Y. If you want to put the symbols in, X is our latitude. So this symbol would be, this is X bar here for the mean. So the average latitude was 38.02 degrees north. The average temperature from our 50 cities, Y bar 27.55. Both in degrees. If you were putting units, I guess this is degrees and this is degrees Fahrenheit, keep them straight. Latitude, so the standard deviation was, this is S sub X, 6.42. Standard deviation for Y, S sub Y, is the 1549. We'll need those numbers. I think we're going to do by hand, coming up with the slope and y-intercept. We'll interpret those values and then maybe answer a few questions. And we're going to go on lunch break after that, so time to eat. Part A, hang with us. What is indicated by the fact that the correlation is negative? Well, I said it already. As you move north, as X increases, temperature tends to decrease. So as X increases, in parentheses, right? Latitude goes up. This means you move north on a map. As latitude increases, X increases, Y tends to decrease. Put that tends to in there. Y tends to decrease. And what the heck does that mean? We expect temperature to decline, right? As latitude goes up, we expect temperature to decrease. It's not always the case. If it was always the case, the correlation would be -1. It would be a perfect relationship. But you can move north and the temperature actually gets warmer. I think up in the Pacific Northwest, they have milder winters compared to somewhere like Ohio, Cleveland, for example, much colder. But I think if you go to Seattle, you're actually more north than Cleveland, but it would be warmer. So we'll put tends to. Okay, part B. Determine the linear regression equation for predicting. I think 2 videos ago I did this. We have to go through the 3 steps. Get the slope first, get the y-intercept second, and then write the equation with words instead of X and Y. So we'll go sort of quickly here. Part 1, get the slope. Part 1, get the slope. Formula is B1 equals R times SY over SX. Okay, we've got the numbers. You can see them on the page. I'll get them right here. Correlation was up at the top in the description. So that was a negative 0.894. Times SY over SX. Make sure we put the S sub Y up top. All right. From the chart, that was 15.49 for S sub Y. S sub X from the chart, that was the 6.42. Okay. Don't lose that negative. We need it. The slope is negative. If you crank that out on your calculator, we trust that you can. You get about a negative 2.16. And that is the slope. So part 1, get the slope. Save that. Well, I'm going to erase it. It's on your notes. So you'll have it. Okay. Part 2, get the y-intercept. If you don't write as fast as I do, you've always got rewind on YouTube. But here it comes. Part 2. Get the y-intercept. We've got the formula. It came maybe 2 or 3 videos ago. Formula, b sub 0 equals y bar minus b1 times x bar. Now, we do need to get the slope first because the slope is part of the y-intercept formula, so we've got the slope. Y bar, x bar come from the chart up at the top. I'll plug the numbers in. Y bar was 27.55. That was the average temperature. Minus, careful, parentheses, slope was negative. Remember, it was a negative 2.16. Negative times negative makes positive when we make this calculation. X bar from the chart up at the top, average latitude was 38.02. Okay? So on your calculator, 27.55, negative times negative makes positive. The answer is 109.67. That's the value of the y-intercept. We've got the slope, we've got the y-intercept. Last thing, determine the linear regression equation. We've got to write it all out. Okay, so part 3 of this process. Here we go. Regression equation. Part 3, I'll even say, here's what we're doing. Write the equation. And remember it's y hat equals b1 times x plus b sub 0. I'm going to jump right to the words here. We're trying to predict January temperature. So temperature. Put a hat on it because it's cold outside and that's a bad joke. January temperatures. It's a predicted value. Let's see here. What do we get? I'm going to write it this way this time. 109.67 minus 2.16 times latitude. The only reason I put the y-intercept first and then minus the slope is because I think that this looks better without having a leading negative out front. You could write this as negative 2.16 times latitude plus 109.67, but it's your choice. It just looks better this way to me. This is the slope. This is the number that's attached to the x variable. Okay, we can flip-flop them if we need to. We just can't flip-flop the numbers. All right, there's our equation. Let me double-check, make sure it's permanently correct here on the video. Looks good. All right, sort of a long part there. We need to start interpreting these values, so let's get to it. Part C, explain in context what the slope of the line means. I'll just leave this up here so we can see it. As I move up 1 degree north, the model is saying that we expect temperature to decrease by 2 degrees, 2.16 degrees. As x goes up by 1, what happens to y? How does y change? So, to interpret the slope, part C, as we travel 1 degree north, moving up on the United States map here, as we travel 1 degree north, we expect temperature to decrease by 2.16 degrees Fahrenheit. It's in context, and it has to be. Put the units. I'm traveling 1 degree north. Temperature is expected to decrease by 2.16 degrees Fahrenheit. All right, so that was C. We'll move on to D. Next page. Explain in context what the y-intercept means. right. All right, college students, y-intercept, x equals 0. We're interpreting the y-intercept. X equals 0 degrees north. If I plug that into the equation, what does the equation say temperature should be in January? Where's 0 degrees north? Of course, it's the equator. Zero degrees north is the equator. Are any United States cities anywhere close to the equator? Think about the southernmost points of the country, like Miami down at the bottom of Florida. Nowhere close to the equator. Check it on a map. We have no data in our data set. It's United States countries. So x equals 0 degrees north is at the equator. We have no data anywhere close to x equals 0. I believe the lower portions of Florida are about, latitude is maybe about 20 degrees north. So we have no data near x equals 0 degrees north. So the y-intercept is extrapolation. The y-intercept is just a point on the line. The point, 0 degrees north. 109.67 degrees Fahrenheit really has no meaning. I have no idea what the average temperature in January is at the equator. It might be something close to 109 degrees, but I have no idea. Okay, this point is just where the line crosses the y-axis. It's extrapolation. There's no data near x equals 0. Okay? You do have to critically think about this stuff. There's no formula we can give you as instructors that will always tell you how to interpret certain things that we calculate in this class. You really have to understand the problems and the context of what we're talking about. Okay, that's D. I think there's a few more. Yep. E, F, and G. Then we'll be all set. Part E, Elkton, my adopted hometown, sits at 39 degrees north. Nowhere near the equator, by the way. Predict the mean January temperature in Elkton. Part F sort of goes with E. It says if a city has a positive residual, what the heck does that mean? All right. We'll do E first. E is just a plug and chug. So, in other words, part E says predict for x equals 39 degrees. Okay? So, our equation was temperature equals 109.54. 67. Good thing I checked. 109.67 minus 2.16 times latitude. For part E, latitude is 39 degrees. I plug in a 39 here. I go to my calculator. I plug this in. Get the numerical answer. And the numerical answer is 25.43 degrees. So the equation based on the data from the 50 cities is telling us that, hey, Elkton is predicted in January to have an average temperature of 25.43 degrees. All right. Part F then. If a city has a positive residual, a few videos ago we said this whole linear regression idea is based on the residuals. If a city has a positive residual, what does that mean? I'd like to draw a picture here. Here's the axes. Remember, x is latitude. And based on latitude, we are trying to predict temperature. Let me put a few labels here. the continental United States, the lowest latitude, the smallest latitude down in Florida, about 25 degrees north. Again, nowhere near the equator of 0 degrees north. The largest latitudes, if you go up to the top of Minnesota, top of Maine, top of Washington states, here's where our latitudes go from about 25 degrees north to about 50 degrees north. Okay? Temperatures in January across the country might range from about 10 degrees Fahrenheit to about 75 degrees Fahrenheit. It's the average temperature for the month for those cities. I don't have the 50 cities. I'm not going to put the dots on there, but I will approximate the line. It's negative slope, right? Negative 2.16 slope, and we might get something that looks like that. Probably not perfect. We're just sort of visualizing the situation. Part F, if a city has a positive residual, what does that mean? Positive residuals means points are above the line. So think of all the dots, the 50 cities, and maybe we have one city that sits right there. Okay? That is the actual temperature of that city. If I go straight across here to the y-axis, this looks pretty, well, it's actually very warm for where it sits, but we'll just go with it here. This would be the actual temperature, who knows what, say 40 degrees, 50 degrees, somewhere in there. The model's predicting, if I go straight down to the line, the model is predicting that that city should have this temperature, right? Here's your predicted temperature in terms of the y. And if I go straight across here, we can see there's a huge difference, and that difference is the residual, right? From here to here, hopefully this is big enough for the video to pick up. But the distance of the dots, up or down to the line, those are the residuals. And so, straight down to its x value, what we're saying is for a city that sits here on the map, whatever that latitude is, the model's predicting the temperature to be here, I guess on the colder side, but in actuality, that city's temperature is much warmer. It has a positive residual, and actual temperature is very different than the predicted. Okay? If a city has a positive residual, what does that mean? Long-winded answer for sort of a short final answer. The city is warmer than expected. Simple as that. City is warmer than expected. The model says one thing, but in actuality it's much warmer there than expected. You could put a part F, part 2, and just say, okay, if a city had a negative residual, what would that mean? The points would be below the regression line, maybe here, maybe down here, and all that's saying is for that city's latitude that the temperature is colder than expected, right? And those would balance out. The regression line would sort of, split all those warmer than and colder than expected line or cities, and the residuals would actually average out to 0. All the ones above the line would sort of cancel out all the ones above, and we get that line that splits all of the points. All right, E and F. One last one to go. Part G, I think. Oh yeah. Last part of this. Part G, what latitude values can we use our model for prediction? I'm not going to erase my picture down here. Can leave this. So we'd like to predict temperatures for various cities. If you check on the map, our most southern points are about 25 degrees north. If you check the map, our most northern points are about 50 degrees north. If you'd like to use our model for prediction, anything in between, no problem. 26.2, 41.99, whatever. Okay? But what we don't want to do is extrapolate. Extrapolating would be, oh, well, let me go down to, say, Cuba, or let me go down to the middle of Mexico, or into South America to see what the model would say. we don't know that the trend continues. Let me go north up into Canada and let me check out Alaska or something, right? That would be extrapolation. So x equals about 25 degrees north to 50 degrees north are okay. It's okay, anything in between outside would be extrapolation. All right, so we sort of summed up everything we know so far about regression. Moving on, things do get a little bit more tricky. So we're going to take lunch. We're going to come back refreshed. We'll see you in class.